So take a moment to decide how you would try to approach this, and then in a minute or so, we'll talk about it.
Hey Matt, I have a quick question about yesterday that I didn't get to ask.
Shoot, what's that?
So when we were doing the cosecant and secant graphs, I didn't catch how you found the asymptotes, how you got them exactly.
Okay. We can certainly look at an example, but the short answer would be the asymptotes occur where the trig function is equal to zero, because our reciprocal of a zero is undefined. So wherever the sine or cosine graph crosses the equilibrium line becomes asymptotes.
Got it. Thank you.
Sure. So just, real quick. Ooh, terrible angle. But if our trig function is doing that through its equilibrium line, anywhere it goes through that equilibrium line is going to become asymptotes. Then the peaks.
That makes a lot more sense now. Thank you.
Sure, no problem. Oop. There we go. So, first step naturally on any question like this would be to draw a bunny rep. So I'm going to do that while you guys work on the problem. Did somebody leave because I was drawing a bunny rabbit? Oh no, somebody came in. Well, I've mentioned before, one of the things we want to try to do as much as possible here is diagram what we're doing. Some people, aren't big fans of graphs. Some people don't think of themselves as visual learners or visual processors, and all of that's fine. But that doesn't change the fact that visual cortex at the back of your skull is the most powerful processing tool your brain has. So anytime we can try to bring it into the game, the better off we're going to be. So it can take a while to get used to making diagrams, take a while to get used to using diagrams, but if you get comfortable doing it, it's going to make a big difference. So population of rabbits oscillates from 22 above and below an average of 52. So that 52 is going to be our midline of the graph we're going to end up with. And we're told we go 22 above that and 22 below that. Notice I'm not worrying yet about trying to write an equation, just trying to get a sense of how this is behaving. Hitting the lowest value in January. So where we put January is kind of really up to us, but then they tell us t equals 0. So that's our t graph. That's our rabbit graph. So at t equals 0, we're told that's our minimum. If that's the minimum, then the graph has to go up from there. And then we're asked to find an equation. So the rabbits are going to, grow, come to a max population, at which point presumably somebody will start trying to eat them. And then, no, I'm sure they will live on the ranch happily for all their lives. And then the population will mysteriously decrease back down to that low value. So how long does that take? What's this period? What should that period be? Is the second low the next January? Yeah, the second low is going to be the next January. So that's January. And what value is that going to be in terms of months? Yeah, that's going to be 12 months because this is oscillating throughout on the year. We're told it oscillates from 22 above to below during a year with its low in January. So every January you have your low amount of rabbits. So if we wanted to take this information and distill it into our information, we have an amplitude. That amplitude is how far we displace from center. And they actually told us that quite directly, that 22. Now that's somewhat unusual. Oftentimes you'll instead be given a high of, what would it be here, 74, and a low of 30. And from that have to determine your amplitude and your middle line. So you should be comfortable working either way. But we're told that amplitude and we're told that lift of 52. So they just give us that information, which is very nice of them. Our period is a little bit more vague in this question. I mean, you read this question, it seems clear that the population is rising and falling throughout the year, but it doesn't ever say that explicitly. So sometimes it's easy to look at this question and say, like, I'm not given any information about the period. And in some ways, you're right. You're not directly told your period is over 1 year, but kind of conceptually, it should be 1 year. And that t equals 0 does kind of give us the impression we should be talking about months. So that period of 12 is an interpretation in this problem. Now, we could certainly have done time in years and called this, our 0th January and our 1th January and our 2nd January and our 3rd January and so on, and made the period 1. That would not have been unreasonable, except we were told to do the problem in months. Fair? Okay, last little piece we would need would be a phase shift, but since this is starting at its low point, we don't actually have to use a phase shift. If we wanted to use a sine graph, we'd have to phase shift it over to that point. But if we wanted to start at that low value, we could use a flipped cosine. either one of those choices should work. We don't even have to actually make the choice between sine and cosine until we get to this idea of how much of a phase shift are we going to have. So if we want to use this as our starting point of our curve, then a negative cosine graph starts there. We wouldn't have to have a phase shift at all. If we wanted to use a positive cosine graph, okay, then we'd be starting here and going that way, which means we'd have a phase shift of that halfway. That's 6 months. If we wanted to use a positively oriented sine curve, we'd have a phase shift of 3 months to get to there, a quarter of the period. So that choice often kind of gets people a little thrown off. Like, I don't know how to tell which one I'm supposed to use. Which one do you want to use? It really is a choice. And the computer is actually fairly good at letting you use different choices. I have found, a couple of you guys have asked some questions, and I found that it's a little bit fussy if you give it things in terms of a phase shift that goes outside, too far outside of the first period. It can get a little persnickety. So, but that's not your guys' fault. That's its fault. It didn't specify where it had to model what. Anyway, so which of those do you want to do? Do you want to use a negative cosine, a positive cosine, or a sine? Cosine sounds simplest, the negative cosine. I think that's true. Anytime you could make this a 0, life is better. Life is better. Oh, maybe make it a bunny. Maybe it's medication. I have no idea. Okay, anytime you can make that a 0, your life is happy. So we're going to have that amplitude be negative. So we have to remember that we've flipped that because we're starting off increasing with cosine, and that's opposite of how it usually starts. So if our amplitude is going to be 22, that's going to give us a 22 cosine. We have to remember to make that negative. We need a B value to adjust our period. We're not going to have any phase shift, so there's no C value. Nice. And that lift is that nice 52. We just got to figure out what this B value is. We do have to, of course, be careful that B value is not 12. That B value is what made the 12. So our normal period is 2 pi, our natural period, divided by that compression factor, that B. If we want that to equal a 12, we got to solve for that B. So multiply both sides by B, divide both sides by 12, and we get a nice B of pi over 6. So negative 22 cosine of pi over 6 t. Again, no phase shift because we're considering ourselves to start at that value. And I do agree. I think that's the easiest way to go. And dink, dink, dink. Yay. So particularly without a phase shift, it's quite a bit nicer. The amplitude goes in there directly. They were even nice enough to tell us the amplitude, and the equilibrium of the value, the lift. Even if they gave us the high-low, okay, we could find the average of them. The average of them would be 104 divided by 2 is 52. So you could average them to find that 52. And then 52 minus 30 is 22. So we can find our amplitude from those quite nicely. Or just subtract those and get the 44 divided by 2 is your 22. So that's your amplitude. So we could have found it from a high-low just about as easily. It's really the phase shifts that cause problems. Before we look at what happens if our population was in April instead, which could bring in a phase shift depending on how we want to do this. Questions about that? I know I did that kind of fast, but let's see, Nick, I think you were asking about some of those on the forums. Did that make sense, or is that part of what was working before, or?
Yeah, I got a good understanding of it now.
Okay.
Yeah.
So let's look at what happens when we change this to April being the low value. Actually, I'm going to make that the 52, and then the 30 and 74. So my x-axis is way down here somewhere. So if our low value is occurring in April, what number would we use for April?
Three if January is 0.
Yeah, the common answer that people try to throw in here is 4, but it's actually 3. Because January is 0, February is 1, March is 2, and April is 3. December is 11, making the next January 12. Fair? So if January is 1, and we're used to counting January as 1, so that always kind of throws this question off a bit. So does that make sense, Shay? It's almost asking for that to be a problem in this problem. So we're going to want that low to be at 3. Then the next low is going to be 12 months after that. So it's going to be at 15. That's going to make our high halfway between those two. So that high is going to occur at 9. These quarter points will occur in between those. So that's at 6 and 12. So if we just consider it that way, then that's what we're told if we think of low, high, low. Fair? So we could, if we wanted to, we could look at this as, well, it's the same graph as we had in this problem. So it's the same as that graph. It's just shifted that way by 3 units. So we could, if we wanted to, just take this answer for part A or part 1 or whatever it was called, take the answer for this and shift it. However, if we continue this graph back one more, it reaches its equilibrium point at t equals 0. So while we could, and there's nothing wrong whatsoever with doing this as a shifted cosine, we could also do it as a non-shifted negative sign. So normally I would say that's going to be beneficial because anytime we can avoid the phase shift is nice. And heck, we could just do it real fast. It would still have the same amplitude of 22. It would still be negative because it's going down first. It would be sine instead. The period is the same, so we're not changing that at all. Still has no phase shift, still the same equilibrium value, and that's the other equation. So that's certainly an option, and probably the nicest option. But if we wanted to practice a phase shift, we certainly could. Our amplitude is still 22. We find the period the same way. Period is still 12, which made our B equal to what was it, pi over 6. And our phase shift here would be a phase shift of that positive 3. Now, again, remember that our phase shift in this form is not this C value. The phase shift, that's better. The phase shift is this C value compressed by the B, right? So if I wanted to find out what the C value is here, one way we could do it, and again, we have options, but if I wanted to find that phase shift, we have to take that C and divide out that compression factor. So that phase shift of 3 has to be C divided by our B, which we found is pi over 6. Multiply that pi over 6 over, we get 3 pi over 6, which reduces to pi over 2. So that phase shift of 3 implies our C is equal to pi over 2. And our lift is still the 52. Now, if you don't like that method of finding the C value in this form, we could certainly instead have said that we've got the negative 22 cosine. Our B is still the pi over 6, but used that internal parentheses and said, okay, our phase shift is that x minus 3 plus 52, and then distribute that pi over 6, and then you'll get the same pi over 6 x minus 3 pi over 6, so pi over 2. So you'll end up in the same place either way, and you'll have to do the same thing to do it. Notice we did this by multiplying those two together, as opposed to here where we multiplied those two together. So it all really depends on whether you kind of like it in the formula on the outside or you like doing it all together in the equation. Either way, as soon as we have that, as long as we remember we've got to flip it, negative 22 cosine pi over 6 x minus pi over 2, do you remember that minus, plus 52, in either way we have of getting that phase shift. So both of these equations represent exactly the same behavior. Just one of them thinks of it, the sine one thinks of it as starting at this equilibrium point and then decreasing. So it's still saying, hey, I'm starting in January. This one is the cosine function is thinking about starting here, but it's been, or starting technically down here, but then it's being pulled back to April. Same graph, same shape, same behavior. If you're not told to use either sine or cosine, either choice is perfectly fine. Questions about that?
Yeah, I have a question. So for our quiz, are we doing it through MyOpenMath?
Yes. Your test? Yeah.
So if we're doing it through MyOpenMath, will MyOpenMath kind of have like, it'll accept both answers, or is it like, because during the homework, it really was looking for the cosine instead of the sine?
It would take, I was kind of playing with it a little bit, it would take both of them, but if you shifted it off too much, like instead of using this shift, you used that shift, it got kind of grumpy about it. So there are two things. One, if the computer gets grumpy, don't panic, for one thing. Because one of the big things you're going to do is, and we were going to talk about this a little bit later, but we'll talk about it now, great, is as you work through your test, you're going to have paper with you and you're going to be working on that paper, right? And do it in a nice organized fashion, number what you're doing, make it as easy as possible for somebody to follow. When you're done with the exam, when you fully submit the exam, you're going to scan that paper, and we can talk about scanning. I have a little of video about scanning. Putting a scanning app on your phone is pretty easy. So you can scan those papers with a scanning app, and there'll be a link to an assignment after the test that is to submit those on papers. Those papers should be, I think I've got listed as should be submitted within half an hour, just to make sure no funny business is going on. So, but I had somebody for the Math 111 test. It took them 45 minutes and they panicked. No, you're fine. it's just to kind of like, don't let it be, 6 hours from then. So just, try to get in as quick as you can once you're done. And then what I'll do is go through that scratch paper, and anything that the computer said was wrong, either fully wrong or partially wrong, I can go through and look at your scratch paper and often go, oh, okay, that's what they were doing, and here's some points back. Sometimes for that Math 111 test, sometimes it was like, oh, no, that's perfectly correct. It's just in a different format. So I can then go through and fix all that. It really helps if it's neat and tidy and well organized. There were some folks who it was very much scratch work. So it was all over the place. I couldn't find anything. So you do want to make sure you're thinking of it less as just scratch paper and more as, kind of the written out version of your work. So there was one person whose score, I think, went from a 20% to an 80%, just because their typing and their interface with the computer was not good. And, that's fine. That's not what this course is about. And their scratch work was very clear, very organized. And I could tell, oh, okay, that's what you were doing. That's what happened. They had a lot of little like 2 times 3 is 5 kind of errors. The computer will say, no, 0. Yeah, I can say, no, that's like 8 out of 10. You just made a little boo-boo. So that usually helps a lot.
Got it. Thank you.
Sure. Okay. Do you want to do another question like this, or do you want to talk about tangent? What's your preference?
Another example like this would be pretty helpful on my end.
Okay. Let's go ahead and do that. There's lots of different types. We could talk about springs. We could talk about, wheels are fun. Let me grab that. That is why I want to use this software. Okay, so you want to build a function that models this scenario. Yeah, it says the function f of t gives the height, but your job is to build that function. And I'll give you a couple minutes to play with that. This is not working. So I hope we all started by drawing a Ferris wheel. Is that true? Did we all start by drawing a Ferris wheel? Did you draw a Ferris wheel with bunny rabbits on it? No? Nah, that's okay. We know it's 45 meters in meters. That's a big Ferris wheel. So 45 meters in diameter. So that diameter is 45 meters. And it's 5 meters. I have a feeling this problem was originally written in feet and somebody just changed the units to meters because these measurements are high. But that's okay. It's got a platform to get on the thing. It's 5 meters high. It's level with the bottom of it. It makes a revolution in 8 minutes, and we're supposed to make a function. Okay, so first job, we want to figure out what is our amplitude, what is our lift, what is our period, and what's our phase shift if we have one. We have to have an amplitude and a period. We sort of have to have a lift. If we don't lift it, its lift is just a zero. That's where its equilibrium is. But we can consider I don't have a phase shift be a phase shift of 0, but we like to not have a phase shift. So let's start with amplitude. What is the amplitude of this function in terms of height? Now 45 would mean it's going from 45 above its equilibrium to 45 below its equilibrium. So that would be a total swing of 90 feet. The 22.5, our kind of equilibrium point that we're going to be above and below, the total distance there is 45, absolutely, but that amplitude is the displacement from center. So the displacement from center is going to be only that 22.5. I think that is trap number 1 in this question, that 45. People love having that amplitude of 45 here. Yes, the radius determines the amplitude, absolutely. What about the period? How long is our period? Got 8 minutes and 8 minutes. Felix and Nick, 8 minutes? Absolutely. It is 8, and that is in minutes, just like this is in meters. So it does 1 revolution every 8 minutes, so it will go from any point to the repeat of that point in 8 minutes. Connor, were you drawing a bunny there? Was that? No?
Yeah, nailed it.
Okay. So, period's 8 minutes. We're going to have to use that to find what our value is for B. So, go off here somewhere and say our 8 minutes had better be 2 pi over our b, because 2 pi is our normal period. Multiply by the b, divide by the 8, and we get a b of pi over 4. So our b is pi over 4. Questions about that calculation real quick and the distinction between the compression factor and our period. I like to think of our period as caused by that compression factor. Now, phase shift depends on where we start. We're told the function gives us height in meters above the ground t minutes after the wheel begins to turn. So that tells us the problem should be in minutes, but it doesn't really tell us where we start. The 6 o'clock position is level with the loading platform, full revolution, and heights meters above the ground t minutes after that. So really, we can say we start anywhere we want. We could say we start, Felix, you're wanting to say we start down here. Now you're giving that a radian measure in standard position of 3 pi over 2, but it doesn't have to be. Because our axis here, our horizontal axis, is going to be time, right? So if we want to start at that 6 o'clock position from our equilibrium point, which we still have to find, if you want to start from that 6 o'clock position, that just means you're starting low. So that just tells us, okay, we're going to want maybe a negative cosine. If we wanted to start measuring our time equals 0 from the 3 o'clock position going up, okay, we go from the equilibrium up. So we'd use a positive sign. If we wanted to start counting at the top, okay, we'd start at the top and go that way. If we wanted to start counting at this position, we'd probably, again, use a negative sign. If we wanted to start, let's say we load people right here. If we wanted to start at some particular angle, well, we'd have to shift for that angle. Felix, I think you're right. Starting from that 6 o'clock position probably makes the most sense. But you seeing what I mean about, I'm not so worried about what this angle is as making sure I am at my lowest point at time equals 0. Then we're going to go through our oscillation and be back to that 6 o'clock position at 8 minutes. So begins to turn, I'm going to say here, from the 6 o'clock. And of course, one of the nice things about that is it eliminates us having to have a phase shift. So, phase shift, 0. So what about our lift? How much is our lift, or where is our equilibrium line? Dominic, 27.5. Perfect. 27.5. We've got to go that 22, but remember the whole thing is lifted 5 meters up. So you added those 5 meters and got our center line at 27.5. And that's going to be 5. And that top part is going to be at 50. So to build our function, this is all our prep work. Usually once we have the prep work all done, making the actual functions fairly easy. But are we going to use sine or cosine or secant or tangent or? We're going to use a cosine. And we could use a sine with a phase shift if we wanted to. But avoiding the phase shift is nice. So cosine. What kind of cosine? Negative, because we're starting at the minimum and going upward with that amplitude of 22.5, with the compression factor of pi over 4 to give us the period of 8. T. We avoided a phase shift. Nice. And then plus 27.5.
Why is the cosine better to use than the sine here?
Mostly just because better is a strong word. Probably easier because cosine by its nature starts at its extreme value and then goes through its oscillation. And this function starts at its extreme value, here extremely low, so our negative, where sine starts at equilibrium and then goes through its oscillation. So if we want to do a sine with this, we certainly could, but we'd have to consider the function starting there after a quarter of our period. So that would be after 2 minutes. So we'd have to put in a 2-minute phase shift, which is fine. And the nice thing, frankly, about that 2-minute phase shift is it would allow our sine to be positively oriented instead of this negatively oriented cosine. So we might like it. And the nice thing is we can do it. We'd have the 22.5 sine. We'd still have a compression factor of pi over 4. And to avoid having to solve for that c, I'm just going to go ahead and put it in the parentheses. So t minus 2, that shifts us over 2 units, plus the 27.5, and then distribute the pi over 4. So it's not, once you get used to doing it, it's not terribly more difficult, but it is an extra step. Fair? So if you graphed both of these functions, they would graph right on top of each other. You put both of them in your calculator, hit graph, and you'll be like, I only see one graph. That's because it's the same graph on top of itself. And yeah, sometimes that phase shift isn't bad. Sometimes that phase shift is worth not having to have a negative out in front of that thing. I don't know, Felix, if MyOpenMath accepts the answers in this form. I wouldn't be surprised if it did accept them in that form, but gosh, I hope it doesn't. Because it really should be having you put it in that simplified form, because that's the form you'll see in physics. That's the form you'll see in most applications. So I don't know, but I hope not. Just because I want you guys to get used to the form you're going to see things in more as you go on. But it's a nice form to use along the way. Usually if I'm going in this direction, going from, because we had the phase shift in this example, we used a phase shift of 2. If I'm going in this direction, I'll do it in those parentheses to do that distribution. But if I have an equation and I'm trying to find the phase shift, I'll just take that pi over 2 and divide by that compression factor. So, which tool should we use? Whichever one's easier for the information you have at your disposal. That's one of the reasons we want our tools to be as flexible as possible. So I don't know, but you can find out. Let me know. Questions about this example? Particularly the end of this section often gets a little bit frustrating from the perspective of can you just tell me the one way to answer these questions? And unfortunately, I can't because there isn't the way to answer these questions. You've got options. And options are good when you're working on stuff, but they can be frustrating when you're learning. I want to show you, while I've got you here, this, where is it? So I'm going to just show you the whole screen. This image that may help it make sense. So all of this is supposed to be about circles, essentially, and rotations or oscillations. So we've got an image here in 3 dimensions instead of 2, but it's looking at this oscillation. So it's looking at that arrow as it goes around and measuring the horizontal displacement, how high it is with this graph over here, essentially being our sine values, while the bottom part, the blue part, is measuring how far left and right that arrow is, essentially throwing out its cosine values. These are basically the same curve because they're measuring basically the same thing. It's just, it's hard to notice because you got to look back and forth, but when this thing is straight up, the sine is going to be at its maximum while the cosine is going to be at its equilibrium. When the cosine's at its maximum, well, that's because the arrow is all the way over, which means the sine is going to be at its equilibrium. So essentially what we're doing is we're trying to model this oscillation. And when you're asking yourself, well, am I supposed to use sine or cosine? Well, both sine and cosine model this oscillation. They just do it a little differently. Fair?
So is tangent the z?
No, tangent is weird. Would it be nice if we had a similar graph for tangent?
I was just curious. I saw that sine and cosine matched up, so I thought tangent might fit in there too.
Well, sort of. That's tangent. That's actually a rotated version of tangent. Tangent is better. I think I have another one for tangent here somewhere. There's links to these. There it is. So this is what what actually looks like when we graph tangent. You're looking at these lengths, but I think this one's hard to look at, and the rotated version is a little bit easier to look at. So this is flipped 90 degrees or rotated 90 degrees from how we will normally look at it. But what we're modeling when we model tangent is this length out here as, ooh, can I make that bigger? Nice. As that thing rotates around. If you want to imagine it in context of something you can actually physically do, if you've ever watched a train go by, you follow, what does your head do? Well, your head starts by looking, almost, not quite, but almost 90 degrees to where you're straight at the track, right? Now you're not looking at exactly 90 degrees because at 90 degrees, you're not looking at the track anymore, right? So at 90 degrees, at pi over 2, that length would be undefined because you can't look at the track at 90 degrees. That's why tangent at pi over 2 is undefined, because there is no length. But any angle in, and you're going to see the track somewhere at a particular length. And as your head turns, that length shrinks to a minimum value and then grows back to a positive value as your head moves, right? That's essentially what tangent is measuring. Fair? So
yeah, and this also repeats on the bottom half of the circle, right? Like we're just seeing the top half.
Yeah, we're just seeing the top half. Yeah. One of the things I like to think of, particularly for the top half and bottom half, is lights on police cars. If you imagine, the light spinning around on the top of a police car, if it's parked in an alley and you watch that light as it goes down the side of the alley, you watch it, it moves kind of slowly and then speeds up as it passes. That light on that spinning object being projected onto a flat surface is what tangent is modeling in one way or another.
That makes a little bit of sense.
So it is a little harder to visualize than, that's always a fun one. We'll get to that when we talk about polar graphing. Anyway, now we'll see it oriented up and down this way, but that is what we're modeling as we model tangent. So let's talk about tangent. Any questions about this example before we talk about tangent? Let me close that. Getting noisy out there. Oh, that's better. Is that better for you guys? Okay. Boy, it's a lot quieter. Okay. So, as you could see, when we model tangent, we're looking at these kind of sweeps that it generates. And again, I recommend thinking about it in terms of like that, the car driving by or the train rushing by. It's kind of going that the sound effects do help. Kind of going and off behind you. So it's that, slowly encroaching, it's not changing much left and right. And then all of a sudden it goes zoom to the other side and then slowly disappears off into the distance. Now, where does it do that? Well, if we look at our circle, the reason this is happening is, and this is part of what I think you were mentioning, Connor, our tangent, we know, is that sine over cosine, right? The y values over the x values. So if we look at what happens at an angle of 0, well, the y value is 0, the cosine value, the x value is 1, so that's why we start at that 0. And then as we increase, our y values are going up while our x values go down. So we're getting bigger y values while we get smaller x values. Well, what happens as these numerators become large and those denominators become small? This gets very, very large. Fair? Now, even though the x and y values are trapped at 1, as this y value gets close to 1, so near a value of 1 on top, and the denominators the x values get closer and closer to 0, near 0, you've got numbers like, say, 0.998 divided by 0.0013. That's a big number, right? That's why you're getting that asymptotic effect happening here. Y tangent gets larger and larger and larger and larger because this ratio is uncontrolled, uncapped, unbound, if you will. But what happens as soon as we hit pi over 2? At pi over 2, that denominator becomes 0, and the whole thing is undefined. I know some of you aren't a big fan, you know who I'm talking to, of the dividing by 0 undefined. But again, think of that train problem. If you're looking down the track and you're looking at an angle, at a particular angle, the tangent is trying to give you that, information about that length. Well, if we look at 90 degrees, well, how long do you have to go down here until you hit the track? You're never going to hit the track. There's no answer to that question. It's not even, people will often try to say, well, that means it's infinite. It's not infinite. That would mean you go infinitely and you'll hit the track. You never hit the track. So there isn't an answer. It's not just it takes infinitely long to hit the track. So this is a nice kind of concrete example of why we can't divide by 0. Because if you look 90 degrees, you can't see the train. Fair? Felix, I was hoping you'd like that. So this sweep happens with its nice asymptote occurring there at pi over 2. Now, if we went in the negative direction, the same thing would apply, except these y values would be negative, the y values would be negative, so these big numbers would be negatives. So it's behaving the same way as we head in the negative direction. It's just that asymptote happens at negative pi over 2 instead. So that asymptote's at negative pi over 2. Now, over in this quadrant, we're going to get the same values, the same small, well, the same bigger y values getting smaller, and the same little x values turning into big x values. But because the x values this time are negative, those ratios are going to be negative, so it's going to repeat itself. It's going to give us those low values again. You remember tangent is positive down in quadrant 3 because they're both negative. Again, same ratios, same numbers. Just this time, since they're both negative, they're going to be positive values. Still undefined when that denominator becomes 0, so at pi. Where there's another at pi, at 3 pi over 2, sorry. At pi, we're 0. So at 3 pi over 2, and we can put another one back here with an asymptote at negative 3 pi over 2. And over and over and over again. So that's, again, this oscillation occurring as it goes around, or if you want this occurring over and over again as we spin over and over again, we just get these repeated big sweeps. Fair? So, an important question here. What is the period of tangent? Ooh, 2 different answers. I got 3 different answers. Nice. So let's look at each of those suggestions. We got pi over 2, we got pi, and we have 2 pi. Any others? Yeah, I know we're over time, but I'm having fun. We'll stop after we talk about this period. So what does the period mean? The period is how long it takes the function to repeat itself. So 2 pi, if we look from 0 to 2 pi would be right there. It certainly does go through all of this, and then it will start repeating itself after that 2 pi. But notice it's kind of doing everything twice in that range. So that 2 pi, while it's valid as a period, it's a little redundant as a period. It's bigger than it needs to be. If we have a period of pi over 2 would be the distance from there to there. And the pi over 2, it's doing a full sweep, but it's not doing both the positive version and the negative version. It's only doing the positive version. So that's a little too small. Not to be Goldilocks here, but that pi is what we're looking for. Now we could go from 0 to pi here and say, hey, this is the up part, that's the down part, but having it broken up that way is kind of annoying. So we generally look at tangent, at one period of tangent, as being one of these big repeated sweeps. Sweeps isn't a technical term, it's just what I'm calling them. One of these big repeated sweeps that go over a period of pi radians. So tomorrow we'll graph some of these more like we did the others before we start talking about inverse functions. And that period, that difference in period, is going to come up when we talk about our periods, because remember, we find our periods by taking our normal period and dividing by the compression factor. For sine and cosine, our normal period has been 2 pi. For tangent, the big difference is the normal period is pi. So we take pi divided by that compression factor instead of 2 pi divided by that compression factor. Fair? We'll talk about that more tomorrow. And let me know if you guys have any questions or if there's anything you need. And have a wonderful day.
Matt.
Yep. Felix, you didn't like that answer for dividing by 0? Or are you just being grumpy because you don't like when I give you good answers for that? That's what I think happens. Option 2. That's fair. I buy that one. All right. You guys have a good day. I'll see you tomorrow.